z, and in that direction there is no magnetic field. It is z of h of z equal to hz equal to 0, but there is the transverse magnetic field is there. Okay, we can't uh, transverse any TEM wave to inside a waveguide, because in order to carry both transverse components we need two waveguides. So in case of TEM wave, the equation is TEZ. It is the electric field along the direction of propagation, and magnetic field along the direction of propagation is 0. Okay, this is the depiction of this TE and TM mode. In this case, the blue lines are perpendicular to this rectangular waveguide, right? This blue lines. This shows that, and this is the direction of propagation. Okay, and to it this perpendicular, which is it is transverse in nature. And in case of magnetic field here, this is shown as a perpendicular to the or transverse to the direction of propagation. It is a TM mode. Okay. And then okay. Okay. Then we discussed this figure. What does this figure shows? Rishikesh, what is this? You don't know? Rishikesh is there? Present? Okay, Devangana, you there?
Yes, miss.
Okay, what does the picture sees?
Half of the sine wave, that is why h10, and
Yes,
next is
yes.
one full half, one full sine wave, so uh,
Two. Hmm.
20, and three half sine waves, so 30.
Yeah, yes. The this this index value 2 and the 3 here and 1 here shows the number of half waves or half sine waves in the waveguide. Okay, in this figure we can see there is only one half of a sine wave here, or a half wave is here. So for one half we write H10. H represents the flux of magnetic field, and here we can see two different types of fields here, or the sine waves, half waves. So this is two half waves. We write H20. Here we got three, so we write H30. We have three different half waves. Okay, this is a figure of TE and TM mode. For TE10 mode, TE1 means M means the number of sine waves in the x, and 0 represents the number of waves in the y axis. That is what TE10 represents. So in the x axis there is 1. That's why we write TE10. Okay. In case of this, the x axis the consists of two half waves. We write 2 here, and there is nothing in the y axis. That's why we write 0. Okay. Similarly, if there is no waves in the x axis, then we write 0. If there is 1, we write 1. That is T01. Okay. So we discussed all these things yesterday. We discussed about this figure. We need to derive the field equations of TE modes in the rectangular waveguides. So for the field equations, we have to write the Maxwell's curl equations in the frequency domain, which is del cross E and del cross H. So you have to by heart these equations. You have to by heart the whole equations actually. These are easy to derive, but takes much time. So if you want, you can by heart, or otherwise you can learn, by deriving. Okay. So these are the equations for the for this TE mod field equation derivation. You need to first learn the Maxwell's curl equation, which is del cross E, and which is equal to minus J omega mu H. And Second is a del cross H, which is equal to j omega epsilon E. Okay. And we have to expand this del cross E. Del cross E, we have to expand this curl equations. So you will get these three equations. Okay, you will get the equations in the hx, hy, and hz form. And in case of TE mode field equations, you have to find the equation for Ex. Ex means electric field component in the x-axis. Ey means electric field component in the y-axis. Ez, the z-axis electric field. Then hx, hy, and hz. This is what you have to derive. So here, from this del cross E equal to minus j omega mu h, you can write these three equations. How? See, if you consider two components, for example, if you consider Ez and Ey, you have to write in this way. Give the partial derivative of dou by of z to Ey, and of y you have to give to z. So if you consider Ez and Ey, you have to write dou by dou y of Ez minus dou by dou z of Ey. Similarly, you can write x and z combination. You have to give the derivation of partial derivatives of Ez to the x and x to z. Okay, you have to find the x component, x axis electric field component with respect to the z, and with respect to x you have to find the electric field in the z axis. And then another combination is x and y. If you take x and y, you have to remember that you have to give the minus sign is very important, so that you have to find which will comes in the right side. Okay, you can't randomly write two of them, you have to check for the sign and write it. Okay, so z and y, x and z, then y and x. Okay, and the answer will be, of course, if you learn this equation j omega mu, then it is easy for to write these answers here. So for dou by dou y of Ez and Ez and Ey, you will get the answer for, you will get as hx. Z, y, the remaining is x, so x comes for the h. Here you write ex and ez, the remaining comes y for h. Here it is ey and ez, the remaining comes for h, here h is z. So this is how these equations are written. Similarly, you can find the equation for in terms of ex, ey, and ez here. So same way, here we wrote Ez, Ey. You can write Hz minus Hy with respect to the corresponding derivatives. We will get the answer for Ex here. And if you take this derivatives with respect to dou by dou z and dou by dou x for hx and hz, you will get the equation with Ey. Okay, this j omega epsilon is obtained from here. Okay, now we like that we obtained 6 different equations. From these equations, we know that we are carrying electromagnetic waves inside a waveguide. So you have to write the wave equation actually in for them. That's why we are substituting j beta g, which is actually a guide phase constant. Guide, G represents a guide and beta is a phase constant. So we give the guide phase constant beta G minus J beta. It comes from the equation e raised to minus J beta G. E raised to any factor represents the wave. It represents a wave. So we get the derivative of this E and H. We get this equation for dou by dou z as minus j beta g. So if you substitute dou by dou z equal to minus j beta g, and we know that it is a TE mode. TE mode doesn't have a Ez component, so we can write Ez equal to 0. For that we will get, after that we have to substitute all this and we'll get these equations. Like here, you know, Ez equal to 0. This is 0, so we have only this component, right? So we have only this component. When this is equal to 0, we have only this component. So that you will get, what you will get? You will get this equation. Beta g. You are substituting dou by dou is it as beta g, and that is dou by dou is at beta g Ey. Then these two minus will cancel and you will get minus j omega hs is this minus j, and this minus j cancels and you will get minus mu hx. Okay, so there will be 3 minus in the equation, so you will get 1 minus at the RHS. Similarly, if you substitute for Ex beta g, Ex equal to mu omega mu hy. Okay, and for dou by dou x of Ey minus dou by dou E is equal to minus j mu hs. Here we couldn't substitute anything, so it happens to be that. Now here you will get equations, and you will get equations here. Again, we are substituting for dou by dou z and E is equal to 0. We'll get equations here also. Okay. So from that we will get this six uh, components equations ex, ey, hx, hy, where h is equal to 0. Okay, so by rearranging everything, you will get equation for ey here, ex you will get for ey, and ey then we put ex, etc. Okay, we'll get for here and here, you'll get this equations here. See, and then we know that for TE mod, E is equal to 0, but HZ is present. So HZ consists, we have to expand this equation to this much bigger equations. Okay, we'll get AM sine m pi x by a plus bm cos m pi x by a into cn sine n pi y by b plus dn cos n pi y by b e raised to minus j beta g z. Okay. So this is what we have to write in your exam. You have to write the field equations for TE mode rectangular waveguides. You will get these equations. Then we have to write the equation for the normal components H. This is the HOZ. We have to find the equation for HZ, which is present in the Z in the direction of propagation, and HZ is present. So you have to write the equation for HZ in case of this is the normal component of H. Z, so HOZ cos of m pi x by a cos n pi y by b raised to minus j beta g z. Okay. Then we can elaborate all the other electric fields Ex, Ey, Ez, Hx, Hy in this terms in this form. So these are actually similar. If you look, you can just find it's very similar to each other. Just the difference in the coefficients only. You can see E0, E0.